Okie doke. Okay, so hello again. So we just had we had matrix hell in the first 8 o'clock session, and now we'll sort of back up a little bit and try to. So I'm going to go over the. So there was a question last time. I think there was a question last time about showing how the T1 solution works. So how can we verify the T1 solution? And I'll go over the T2 differential equation solution, maybe to make it slightly simpler. So the T2 solution, that was page 1 of the differential equations textbook, and the next one is basically page 2. That's as far as I got. So we're not gonna be too hard. So just to redo the argument for how you get the T2, how you verify the T2 decay solution. So we'll write the Bloch equation part. So the solution, or the differential equation just was basically the xy component divided by T2. We wrote it out with the vectors, but basically we're interested in the length of it. And so if we sort of make it more faceless, so we just have a function of time, we're taking the derivative of it, and that just equals the minus 1 over T2 times the function. So I just rewrote it sort of in a more faceless form. So it's just some function of time that when we take the derivative of it, the answer is 1 over T2 times the function. And when you solve a differential equation, what you're trying to do is find out what the function is. So this is the unknown. And we said that the answer to that, the answer to it was the starting magnetization just after that point in the xy direction times e to the minus t over t2. And so then this is the solution. So this is differential equation. This is solution. And then the question is, why is that a solution? And so the way we test whether it's a solution is we take the derivative of this guy and just see if it equals this. So how do we take the derivative of that guy? So now let's just go take the derivative again. And what we have to do is we have to take the derivative of the exponent, so that's minus 1 over T2, multiplied by the thing, so that's m xy 0 plus e to the minus t over T2. And now we see whether that is correct. And so how do we see, I kind of did it in a complicated way, but how do we see that that's correct? So here's our answer to the derivative. And so that thing should be equal to that. And how do we verify that it's equal to that? Well, what does that say? That says the derivative equals 1 over T2 times the function. What is the function? Well, the function's right here. And so that's that thing. So if we substitute that in for the function, we can see that this thing is correct. So when we've taken our derivative, we end up with something that is 1 over t2 times the function. Here's the function. So here's 1 over t2 times the function. So that was less substitutions to try to make it a little clearer. So again, what we're solving for this unknown function. So we don't know what it is, and here's the answer. And then here's how we verify that it actually is the answer, because we take the derivative and we get back to this. So that's the absolute, like I said, that's page 1. So that's the absolute simplest. But what if we have one more thing in there? One more fly in the ointment. So what if we have like the T1, the T1 case. So the T1 case is a little more complicated. So I'll just go through how that one is derived. It is not on the test. This is just to give you an idea that it's possible to actually work your way back from the T2 solution also. So this guy is T2. So now let's do T1. I'll try to keep it at the same height. So for T1, we'll write out the equation. So the equation was dm dt, and we're leaving out everything except for the mz minus mz0. I'll leave out that vector, and that's divided by T1. So we could just rewrite that to make it more like we have over here. It's just 1 over T1, so minus 1 over T1 times mz minus mz0. Okay, so that's the equivalent of the equivalent expression is a little more complicated. So this is T1 case. Okay, so now if we write it out sort of more generically, so we can sort of think of it more like a simple equation. So the derivative of the function, the derivative of the m function, that's what this is. This means derivative. Okay, so that derivative is equal to, this was our answer, it's mz0 times 1 minus e to the minus t over t1. And then we have that other thing, which was whatever the starting magnetization was in the z direction, also with that same decay term. So for the purposes of for the purposes of comparing it to taking the derivative, sorry, that's not it. That was the solution. Let me, I did this wrong, sorry. It's supposed to be one further down. Okay, so first thing we want to do is just write this out sort of more generically. That's what I meant. Sorry about that. So that would be, minus 1 over T1, sorry guys, times our unknown. So here's our unknown, minus mz0. Okay, so now we have sort of a generic version, but now our unknown, instead of just being multiplied by something, has something subtracted off it. So this is unknown. And the answer to the unknown, which we said was the one that I had up there before. So the answer to the unknown was, mt without the dot on it. So this guy, remember this is derivative. So now we have mt without the derivative on it, and the answer to that one was what I had written out. So that was mz0 times 1 minus e to the minus t over t1 plus the mz, whatever we started off with, times that e to the minus t over t1. So now the question is, why is that the solution? Can we take the derivative of this and show that the derivative of this mess turns back into this. So how we do that, let's just rewrite this, separate out the separate out the mz0. So mz0 times 1, and then minus mz0 times e to the minus t over t1. I just distributed that, plus mz, whatever we started with, times e minus t over t1. So now let's take the derivative of that. And so how do we take the derivative of that? So to take the derivative of that, first we take the derivative of each term. So the derivative of a constant, this guy's a constant, is 0. And the derivative of this guy is going to be like we had before. It's going to be basically plus, because we're going to get a negative from taking that negative out there, and another negative. So plus 1 over t1 times the whole thing. So mz0 e to the minus t over t1. And then we have to do the same thing with this guy. So this guy is now going to have a minus because of the minus coming out here. So minus 1 over t1 times this whole thing. mz0 plus e to the minus t over t1. Okay, so now we calculated the derivative of our solution, and this thing should be equivalent to this. Now you're going to say, like, but what about that mz? What's that mz0 doing in there? How does that work? So the way to if we sort of like do the same substitution that we're doing here, so this guy with the mz in there, see, that guy's got an mz in it. That's our solution. So that guy is equivalent to that one. And so now the question is, why is this one that doesn't have it in there? So let me just write this out one more time to make it slightly clear. Just pull the 1 over t1 out. So if we pull out a minus 1 over t1 out, and then we're multiplying by a minus mz0 times e to the minus t over t1 plus mz, whatever we started with, e to the minus t over t1. Okay, so this whole thing is supposed to be the derivative. And so if we go up, that one is supposed to be equivalent to this guy. And so is it equivalent to that guy? Yes, it is. We got the 1 over minus t1 is there. And then we just have two terms here, but we subtracted off this mz0, and so that got rid of this guy. So basically, the way to think of it is that this equation says, the unknown function, whatever it is, minus mz. So here's our unknown function. It's got an mz0 in it, and so we subtracted it off, and so then we get this, and that thing is equivalent to the derivative that we calculated. So you can see what the problem is with differential equations. It's all the substitutions that you have to do, because you're sort of abstracting back and you're solving for an equation instead of solving for a number. So I don't know if this was helpful, but if you can sort of, this one's easier to understand. That's page 1, and then this is page 2. Like I said, I only got to page 2. I only got to page 2. So you're doing well if you can get to page 2. So this one's easier to understand. This is just another version of it, but it's got this additional term in it. And so that's why this thing, sometimes written this way, is a solution to this differential equation, and here's the part that we're solving for, the equation that fits into this unknown equation. So unknown equation. Okay, so hopefully that wasn't... I'm going to make up I don't have a page of notes on this. I'll make up a page of notes and add it to the notes so that this will all be written out cleanly in that in a page of notes. So, okay, so that's the that's sort of verify that the our T1 solution. This is this is the one that you'll use in the homework. So that this is like for the. We'll take that one out for homework. So that's the useful equation. So whatever the magnetization that you start with times this thing, and then whatever your equilibrium magnetization times this 1 minus that thing. So that's how you would calculate if you're doing a T1 contrast problem. You'll need this equation multiple times. So yeah, so I mean the bottom line. These are the bottom lines. These are the actual ones that you use in the homework. So to some extent you can ignore all this, but this is just trying to explain where they came from. Okay, so moving on. The next thing I want to do, I sort of talked about it just briefly in the, maybe I'll just see, is there any burning question here? Burning question here. No. No burning question. And I'll also leave some time at the end so we can have some questions at the end as well that won't be recorded. Okay, so now let's just talk about the full block summary, because one of the problems here is, here we're just dealing with T2, we're ignoring everything else. Here we're just dealing with T1, we're ignoring everything else. How does the whole picture fit together? And sort of more importantly, how can we just consider T2 and ignore T1? Why is that? There's a specific reason for that. So what we'll draw out, so initially we drew out pictures that look like this, where you have the B field, and then here is the M field, the M vector, and then they were processing around like that and sort of moving in that direction. So we're just going to draw a big version of that. So the big version of that is, so here's like a really big, here's a big, really big B0. And then here's the hole in the plane, and here's so here's a nice big plane. So you've got a lot of room so the vectors are not confused with each other, all crammed in there. Okay, so this is the B field, and so when we include everything, when we include precession plus T1 decay plus T2 decay, what does it look like? So, so here's the M vector. So the current state of the M vector. So we just put this guy here. So that's the M vector. So the first thing is the precession part, sort of the M cross B part. And so that part gives you an update vector like this. So that guy, this guy was dm dt from precession. M cross gamma B. So if nothing else was happening, this would just keep going around. It wouldn't change at all. But then we also, and it's going around very fast, and so one thing to keep in mind, not drawn to scale. So components. Not drawn to scale. And why do I say that? Well, this guy is whipping around 100 million times a second, so that vector is going to be quite big. The vector that is the T2 and the T1 decay are changing on the rate of like 1/10 of a second or a second, so they're 100 million times smaller. But it would be difficult to draw on the board 100 million times smaller, so I'm going to draw it the same size. But it's not to scale. So that 100 million times smaller T2 decay vector is going to be in this direction. So it's in the plane. No, that's the wrong perspective. I gave you the wrong perspective. So this guy's in the plane. So and where is it heading? It's heading toward the center right there. So it's in the plane, heading toward the center. So it turns out that vector is perpendicular to this vector, always. So if you think about it, no matter where you are along the circle, if you point toward the center, you're always going to be perpendicular, like the tangent to the, anywhere along here, it's always going to be perpendicular to the vector that's going to the center. And so when it's perpendicular like that, that's handy, because that means we can sort of ignore, since any change that this vector does won't affect, the vectors can sort of be dealt with independently because of the fact they're perpendicular. So this guy is, the dm dt component from the, mxy divided by t2. So that's the T2 decay that's getting tacked on to the vector. And then last but not least, we have another vector that's perpendicular to both of those two. So that vector, it's perpendicular to this guy, but it's also perpendicular to this guy, to this one right here. So if I drew it over here, you'd see it was perpendicular to that one also. So, the z direction, no matter where this is around the circle, it's going to be in a horizontal plane, and so the z regrowth, the T1 regrowth is always going to be perpendicular to. So they're all perpendicular to each other. And so this guy is the dm dt from the, mz0, minus mz0 divided by t1. And that's, sorry, I forgot the minus. So that ends up being a regrowth. It's a subtraction here, but since we're subtracting off the equilibrium magnetization, which is the maximum, this number is always negative. We take the negative of it, it's a positive, so that's a growth. So what does that finally give us? That finally gives us the full dm dt. So this guy, not drawn to scale, is the full dm dt. So this guy was, the dm dt component in the regrowth direction. This is the perpendicular to that component in the decay, the T2 direction, and this one was the component which was in the precession direction. So this is the full Bloch equation now. You see the full Bloch equation. So this guy is the real update vector. So it includes, both precession plus a little bit of decay plus a little bit of a regrowth. Okay, so hopefully that should now be cemented together into one coherent picture that sort of makes sense. So now what we want to do, so that was T1 Bloch equation summary. So let's just talk about simple matrix operations. And like I said, this is the introductory lecture for the one I gave the last hour. So this is, what do matrices do to vectors, and what kind of matrix? And then I'll talk a little bit about talaracking, like how does the talarac matrix work, where you might have some translation in there too. Okay, so the first question is, what does, let me erase this too. So the first question is, what is a matrix? What's the geometric way of thinking about what a matrix is doing? Because it's always good to sort of think in geometric sort of 3D terms. We're 3D animals. And so the basic idea, is that a matrix can do just two things to a vector. So it can rotate it and or scale it. A vector. And how do we write this out? We write it out as, if I write out bold letters to mean a vector, so if I make small letters for vectors and then bigger letters for a matrix, and I'll put a little matrix sign on top of it, times a vector. So a matrix, so when you see something like that, what you think is a matrix rotates and scales a vector. So here's the vector that's being operated on. The matrix is doing some operation to it, and the result is another vector. So how do you actually just write that out in terms of components? So if we have our coordinate system here, and we've got one vector, so here's our one vector, the A vector. So for that one, we can decompose that into its components, and so here's its components. So there's one, there's another one, and there's the third one. So those are the XYZ components. We'll put our standard sort of X coming out this way, Y and Z going up that way. So then we have some other arbitrary output vector, so we'll put that guy over here so that I don't overlap the components. So here's our output vector. So this guy was A, this guy was B, which is the output. And we can break that one up into its components. So that guy, say, that guy is, we have to move this axis out here. So that guy is, see, that guy's in the back quadrant there. So here it's coming. So that's one of the components. And here's the negative x-axis, negative x, this is negative y. Okay, so here's the negative x component, so there's that guy's x component, it's negative. And then finally, here's that guy's z component. Okay, so we got all our three. So we got 1, 2, 3, 1, 2, 3 of our components. So what is the actual sort of, matrix operations when we multiply things? So the x, y, z components here are equal to our 9 numbers. So here's, matrix 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. And we're multiplying by our a, x, a, y, a, z. So what are the rules for doing this? So the rules for doing this is we take the first row and multiply it by the first column here. There's only one column. And so m11 times ax. So let's just painfully write out just a couple of them. So bx is going to equal m11 times ax plus m12 times ay plus m13 times az. And then by, we won't write out bz. Same thing, but just second row. ax plus m21 ay plus m22 23 times az, etc. Okay, so what does that do? So that just looks like a mess. You just multiply all these things. But the end result is it moves this guy over to here. And in the process, it might have, so it rotated some arbitrary, direction to some other part of the space. It might have shrunk it or extended it also. So that's the rotate. So it may or may not have rotated it, and it may or may not have scaled it. Just depends on what numbers you got in here. So that's the first geometric picture to have in your mind. When you operate a matrix on a vector, so remember matrix is before, so matrix times a vector, it rotates and possibly scales it. Now, the first thing you might think of, well, is what about like something like a telluride transformation? Because you're trying to line up a brane with another brane. How does that work? So say you have, you've got some coordinate system, and you got a brane sitting in there someplace. Say it's right over here. And say we want to line that up with another brane, some other brane, and say that other brane is like, over here. It's not lined up. It's rotated. And say, let me just do it again so we put some scaling in there. So say we've got a big hulking brane over here, and we have another smaller brane, small but powerful brane that's over here. It's not only different in size, it's, maybe it's a little plumper, it's a little bigger in this direction than this one, but it's also offset in space. Its center is offset. So how do we deal with that? This kind of matrix can't do that. This kind of matrix can only rotate and scale a vector. It can't sort of translate the base of the vector somewhere else. And we need to do that if we're doing like an alignment between a brane. And so how does the basic sort of telluride alignment or basic sort of three-dimensional alignment between branes work? And so, so add, translate. Well, it's kind of like a standard. I kind of think of it as a bit of a hack. So so it's kind of a hack, and you'll see there's an official word for it, but it's sort of a hack, and it can cause trouble when it comes to dealing with the translation part versus the rotation and scaling part. So how do you do this? Well, we just go to a 4x4 matrix. So we start off with our output vector, which is our, aligned brain vector. You can think of each, so that's a brain. What is the vector? Well, the vector is, the vector to one of the points in the brain. And what we want to do is figure out, let's get, this point in this guy's brain aligned up. And so we want to sort of rotate that vector over to that guy. And if you apply that to every single point in the brain, then this same matrix to every single point in the brain. So basically, this is, every point and a single, point in the brain. If you apply that matrix to it, then it will sort of rotate all those vectors into the right place, a single point, for example, in brain. Okay, so what does this hack look like? So here's the BX, BY, BZ, that's our aligned brain. And then we have a 1 down here. Okay, it's always a 1. And so what that is equal to is a matrix that has a 3x3 matrix in it. So here's a 3x3, like one of these guys. So this is 3x3, rotate and scale. And then we have our fourth one. We'll call this dx, dy, dz, and that's our translation. So this guy is our translation. And then there's zeros down here, and there's a 1 down here. Okay, so that's a matrix. So that's a 4x4 matrix, or you could sort of think of it as it's 3x4 matrix, because this guy is always going to be 0, 0, 0, 1. But how does that work? So that has to operate on something, and so what it's operating on is our A vector, like it was before, AY, AZ, and you got a 1 down here. So what does this do? So what this one does, it's important to have the order. So what this thing does, this matrix does, is it rotates and scales. And so that would be like sort of rotating the brain into alignment and scaling it, because this one's smaller, so we got to stretch it. So it rotates and scales, then it translates. And when you look at one of the multiplications, you can see, why that is. So if we've got, there's 3 numbers here, and so when we're calculating BX, how do we do that? Well, we take these 3 numbers and multiply them by these 3 numbers, and that does the rotation and scaling of the X component. Here's the rotation and scaling. And then we add 1 times dx. So it's just like, bx times this one, by times this one, ax times this one, ay times this one, az times this one, and then 1 times dx. So then that will sort of add a translation onto it. Now, why is the sort of then part important? Well, if you do these in the wrong order, it won't work. So say, for instance, we we wanted to change the rotation. If we just try to rotate the brane using a matrix without taking into consideration that we already translated it, it won't work right. So what's the example? Well, so say you have a brane here and say it's sitting up here. Okay, and say we want to rotate that guy a little bit to sort of line it up with another brane. If I just rotate it when it's offset like that, then what's going to happen? Well, you know, say I rotate it this way, well, it'll just sort of go over to here. But I didn't really want that. What I really wanted was to undo the translation, rotate, and then redo the translation. So that's the thing you have to watch out for. And if you've messed around with imaging software, you've probably run into this kind of situation where suddenly, like, the brane's like, way far off. You thought you were just maybe rotating a little bit. So how would you do that? Well, first you would untranslate the brane so that it's so what you do is untranslate, so you're centered again. Then rotate. So now we rotate centered, and then retranslate. So this is, untranslate, rotate, retranslate. And like I said, it's kind of because of the hack thing. So what does a matrix do? A matrix really just rotates and scales around the the center of the coordinate system. And so when we build in the translation in this kind of hacky way, we also have to make sure that we sort of don't do it in the right order. And so if we just want to rotate the brane, if we just want to translate the brane, we can just update the translation. But if we want to rotate, we have to sort of untranslate, rotate, and then retranslate. So that doesn't explain how you actually calculate the matrix. So this was just using the matrix, using the Telerik transformation matrix. So to calculate it, what you're going to do, you have to do is like compare the branes to each other and then just see how different they are and figure out which direction you need to go to make them better lined up. So that's a whole different thing. All we're doing is just trying to understand how the matrix works in the first place. And so this kind of a matrix is commonly used. It can only do a linear transformation. And so let's just say 1 second what a linear transformation is. So a linear transformation, no bending. So one thing we can't do, we can't take a brane like this and bend it so that it sort of resembles a bent brane. Can't do that. We can make a linear approximation to it. And so what is a linear approximation to it is, well, we can stretch it uniformly in one direction, but we can't actually bend it. So we can just, if we stretch it, it just has to be stretched uniformly across the whole space, just like this matrix will do some kind of rotation and scaling to every vector the same way. So no bending involved. You need more numbers for bending. We only have 12 numbers. We only have 12 numbers here to work with. So 12 numbers. But it's a very nice, well understood kind of way of lining branes, and it's still used. It's still used a lot in neuroimaging. And most branes aren't too bent. Okay, so for the final insult, let's just talk about the thing I was using in the previous lecture, which is a rotation matrix. So what if we want to just, so this matrix right here that I drew up as a general matrix, it can rotate, it can scale, do some combination of them. But what if we want to just rotate something? And this is important in MRI because a lot of times you might turn on the RF and you say that I just rotated the magnetization, around the x-axis, something like that. So let's just draw up that. So say I just want to rotate like this around the x-axis. So here's the x-axis and z and y. So for instance, I've got a magnetization vector that's like this, and what I want to do is just rotate that guy around the x-axis without doing anything else. So how do I do that with a matrix? And that's a special kind of matrix. We just draw it out, what it looks like. So here's the matrix that you need to rotate some arbitrary angle around the x-axis, but don't mess with any of the other rotations. Don't rotate it around the x. Don't rotate it around the y or the z, and then also don't change its length. So that's why just rotate it without doing anything else. And the matrix that does that looks like this. 1, 0, 0, 0, cosine of that angle, sine of that angle, minus sine of that angle, cosine of that angle, 0. So what that thing will do is actually just rotate something by however many degrees. So this is, I want to rotate it 45 degrees, so you just put cosine of 45 in there. And then just multiply that, times some arbitrary, vector. So here's ax, ay, az. So this, if you just do, 1 times a, 0 times ay, 0 times az, then do this, you'll end up with just a pure rotation. And so you can, if you look in the notes, you can see examples for how you rotate around the y. One of the things, again, the order matters. And so if you rotate around the x and then rotate around the y, that's not the same thing as rotating around the y and then rotating around the x. So the order matters. And so if you want to rotate around an arbitrary axis, so say you just have like, some, vector right here. And what if I just wanted to, rotate around like an arbitrary axis like that, that's not lined up with the coordinate system. Say this guy is, projected down to here or something like that. How do I do that? That's a little bit more of a pain. So one way of doing it is get rid of all, put this guy back up on the z-axis with some transformations. So, undo his movement away from the z-axis, rotate around the z-axis, and then redo it. Kind of similar to untranslate, rotate and scale, and then retranslate. So that's one of the problems with these rotation matrices and just understanding rotation in 3D objects. If you just get a little, like a little die or a little cube that has distinguishable faces and just try, like, say, rotate around the x-axis and then, so, say, rotate around the y-axis and then rotate around the x-axis, and then try it again. So, like, rotate around the x-axis and rotate around the y-axis. You'll get different things depending on what order you do it in. So, so that's once you sort of see what's out there, then you get a sort of a feel for it. It gets a little easier. Okay, so that's it for the recording part. So these were simple cases of thinking of a matrix as, when a matrix operates on a vector, what it does is it rotates and scales. It doesn't move the base of the vector. And then we talked about how you could sort of put translation in there. And then these are special cases. These are special cases, and these columns here are orthogonal, which means at right angles to each other. So if you think of those guys as vectors, if you want a rotation matrix, these guys should be perpendicular. So you can work it out for simple angles, like just try 90 degrees in here, and you'll see that this vector will be perpendicular to this one, perpendicular to this one. So you can think of each of these guys as a vector. That's another way of thinking about a matrix. Okay, so I think we've come to the end of all of linear algebra, not very well in 30 minutes. So I think we'll end the recording, David, and I'll wait for some questions.